Good day, everyone. In this video, we are going to have a code na walkthrough about the implementation of logistic regression in Python. So we are going to use standard libraries like NumPy, Pandas, Matplotlib, Seaborn, etc. And we'll also be using sklearn for preprocessing, building the model, and for validating the model. So in order to validate whether our algorithm from scratch is working correctly, then we will check our results on the breast cancer dataset, wherein the breast cancer contains some information about a certain tumor, like its radius, texture, perimeter, area, smoothness, etc. So each of the tumor has a corresponding diagnosis, which is M for malignant and B for benign. Now, first thing is we are going to drop some information. So like the anim 32. So if we check the column, it is composed of non-values. So we are going to remove that. And then we are also going to convert this M and D na diagnosis into corresponding 1 and 0 na values. Okay, so we'll convert 1 if M, else 0 for each diagnosis. So if we check, sorry, let us quickly rerun this. And then if we check our data frame, now the diagnosis is composed of 1s and 0s, and the anim 32 is now dropped. Now preparing the X and the Y na values. Okay, so we have the Y, which is from the diagnosis column, and the X data is all of the columns except the diagnosis. So we simply drop the diagnosis. And printing Y and printing X data. So we have the X data. Now the problem here is there are some columns that are of different scale. So suppose we have the area mean, and the area mean is have values that are more than 1,000, right? And there are also features that have values less than 0. So if we run this, or if we use this data set, the tendency is more importance may be given to these values that have higher values, while less importance will be given to those features with lesser values, like less than 0. So it's important that we need to standardize the data to put them into one scale. Okay, so what we can do is to use this standardization formula, wherein we subtract the data with the minimum divided by the maximum and the minimum. Okay, and then so it will give us a standardized information. Standardized data. As you can see, they are now of the same scale. And we are also going to insert another column bias that is composing of all ones. So now, after doing a standardization, we can now split the data set. And in other words, split the data set into train and the test size. Test. So we are only going to use the train for fitting the model. So in here, we are assuming that the test size is 25%. So it will give us a X and Y na train and test. So this train data will be used for fitting the model. And now we will discuss how to train logistic regression and how to implement that in Python. So for computing or for classifying a certain instance, we must compute for its probability. So for example, given predictors like area, perimeter, etc. So what is the probability that a certain instance is malignant? Okay, so in order for us to compute for the probability, we must compute for the weighted sum of the predictors and the weights. So the predictors here are the 31 columns earlier with the bias, okay? And then each of the predictors will have associated weights, and we will take their weighted na sum. So simply by taking the dot product of the weights and the predictors. And from this, we can introduce a nonlinearity because this one can produce values that are greater than 1, and we want to estimate probabilities, and probabilities are only within the range of 0 and 1, so we can convert it into an S-shaped form which has only values between 0 and 1, and we can do that using a sigmoid function which has this form. Okay, so implementing this in Python is pretty much straightforward. So first is this sum, and we can do that by the dot product of x and w, or this is just the weight, okay, or the theta. Okay, so note weight is simply the theta. Okay, now the sigmoid on the other hand is 1 over 1 plus e raised to negative z. So z in this case is the weighted na sum. So after computing for the probabilities, we can now classify. So if the probability is greater than or equal to 0.5, then we can classify a certain instance as 1. But if less than 0.5, then we can classify a certain instance as 0. Okay, and for predicting, then we take the sigmoid of z, which is given by this one. And in this case, the z is the weighted sum. So we compute for the sum, set that to z, and pass that to the sigmoid function. Okay, and it will return as the probabilities. And if the probabilities are greater than 0.5, then we can set it as 1, else 0. Okay. And now, after computing for the probabilities, in order for us to assess this, then we must calculate for the cost. And the cost function is simply the average cost for all samples. And there, for logistic regression, the cost is log loss or binary cross entropy na loss. So if the predicted na y is equal to 1, and this is just for a single instance, okay? So if as predicted the y for a single instance is equal to 1, then the cost is negative log of p. But if the predicted na y is equal to 0, then the cost is negative log of 1 minus p. Okay, and we can represent this into only one equation given by this one. So we have y times log of p plus 1 minus y times log of 1 minus p, wherein the p is the log of p is the probability if y is equal to 1, and this log of 1 minus p is the probability if y is equal to 0. So this is basically equivalent to this representation, okay? Because if y is equal to 1, then the second term will be canceled out. But if y is equal to 0, then the first term will be canceled out, and we will be left with these values, okay? And as mentioned, we must compute for the average cost of all the samples. So as you can see, we are taking the sum of all the cost and dividing it by the number of samples. And now, this cost function must be minimized. And in other words, if the true na value is, or true na label, or true classification is equal to 1, then we want that the probability will also be as much as possible close to 1. Okay, so because if the probability is far away from 1, then the tendency is the cost will also be increasing. But if the true label is equal to 0, or in this case, if the true label is benign, then we want that the probability will be close to 0. Okay, and the global minimum is also 0. So because as you can see, if the true label is 0 and the probability is getting closer to 1, then the cost is also increasing. And in order for us to minimize this cost, we must find the best na theta, or the best na optimal na weights. So what can we do? Compute for the new weights. But before that, let's discuss how to implement this into code. So first is we simply compute for the first term, which is y log p, and then the second term, which is 1 minus y times log of 1 minus p. Okay, and we take their sum of all the samples and divide it by m in order to take the average. Okay, and now let's compute for the new weights. So how do we compute for the new weights? So to compute for the new weights, we must do some changes to the theta. Okay, so we are going to compute for the partial derivative of the cost function. So this is the cost function. We must take the partial derivative with respect to the change in weight. So essentially, we are going to nudge the weight a little bit or find a better weight such that the loss will be or the cost j of theta will be minimized. Okay, and the partial derivative of this cost function is equivalent to this. So we have the sum of all the error times the x values. So essentially, this error is simply the difference between the estimated na probabilities minus the true labels, which is either 0 or 1, multiplied to the x and dividing by m for taking the average. Okay, so this partial na derivative will tell us the direction as well as the step or the change in weight. So implementing that into code is pretty much straightforward as well. So we have this summation, which is equivalent to the dot product of this difference in this x na values. Okay, so we implement that using numpy and we return the gradients. So we now have the partial derivative. So now we must update the weights until we reach the number of iterations. So in order for us to update the weights, so we simply nudge the weight a little bit minus the learning rate times the computed gradient or derivative, which is computed using this code. Okay, and we must do this repeatedly until such time that we reach the number of iterations. So let us try to see it in code. So we have this for loop that does the gradient descent. Okay, so we will repeat it with a certain number of iterations. And so after computing the gradients, then we can now update the weights. Okay, so this is pretty much equivalent to this part. So we're in the weights minus the learning rate times the computed na gradients. Okay, in which it came from this function. And now we have this continued until such time that we reach the number of iterations. So suppose we have a here run, we have a 500 na epochs or iterations with the learning rate 0.8. So we are passing here the initial na weights So in this case, the initial na weights are all zeros, or you can actually set a random na weights. That is also possible. And then passing the X train and the Y train, because we are going to fit only using the X train. And then the number of epochs, assuming is 500, and learning rate is 0.8. And these are the weights that were returned. So let us try to print how the probabilities look like. Sorry, print P. So as we can see here, initially the probabilities are set to 0.5. Okay, but as we continue, then the probabilities are getting closer and closer to the true na labels. Okay, so we return the weights and as well as the cost. So these optimal na weights will be used for the prediction. So we are going to predict, let's say, the X train, and then evaluating the predictions, and it will give us the accuracy of 97%, and precision, recall, and F1 support. And if we plot the cost, then it will give us this convex na form or plot. As you can see, the cost is decreasing as the number of iterations is also increasing. And then for the test na pred, so we also use the optimal na weights, the X test, and the accuracy score is at 98%. Okay, so what if we increase the number of iterations to, let's say, 1,000? So the weights have changed so far, and rerun. And as you can see, the accuracy for train has pretty much improved. Okay, and then if we plot the cost, then there is also a little bit of change on the shape. And then if we predict the test, then it gives us relatively similar results. Okay, so now for the sklearn implementation, it's very much straightforward and easy. So we simply have to use the logistic regression, which is available in sklearn.fit. So we are fitting the model and then passing the train data. And this fitted the model, we will be using that to do predictions. So let's say predict muna on the X train and then evaluate predictions, and it gives us these results. And we can also use this fitted na model to do predictions on the X test. And this gives us these predictions. Okay, and that's it for today.